Alright, here we go. We just finished the big pot of soup problem, and now we're going to be looking at a second Newton's law of cooling problem. And I'm going to take this as if it's the first one. In other words, you'll see it from the very beginning. If this were a problem on a test or a quiz or the AP exam, you can see what you would have to do from the very beginning. So we're going to act as if, I'm going to act as if we have not just done a big pot of soup Newton's law of cooling problem, so you can get the explanation again. So you should have already tried this problem as it was a homework problem, but you might have still had trouble with it. So let's see how we do. So we start off by understanding that this is a Newton's law of cooling problem. In other words, if we want to remember Newton's law of cooling, and like I said in class, I want you to not just memorize this formula. What I want you to do is understand what it means. So yes, you do have to memorize the formula, Newton's law of cooling, but what I want you to be looking at here is I want you to be looking at the fact that this y prime represents the rate at which the temperature of whatever object is changing. So the rate of change of the temperature is proportional to the difference between the current temperature of the object and the surrounding temperature. Okay, so this is again a differential equation. In fact, it's a separable differential equation. And the one thing that we want to do first is be able to solve. We want to solve the equation for y. We want to get y as a function of t, time. And in order to do that, the first thing we're going to plug in here is that our surrounding temperature in this particular problem is 20. Okay, so here we have a separable differential equation, and I also want you to understand that that y prime is actually dy dt. So y prime, meaning dy dt, equals k times y minus 20, which helps you see the separation a little bit easier, I think. So we've done this enough. You divide both sides by y minus 20, multiply both sides by your dt, and here we have our separation of the variables. That gets you a point on the AP exam. Getting the correct antiderivatives for each of these gets you another point on the AP exam. And we know by now we're getting the antiderivative of 1 over y minus 20 dy. That is ln of the absolute value of y minus 20. We could have done a u substitution, but du is the same as dy here. So understanding that if that were 20 minus y, then the u substitution would have yielded a minus sign in front of that ln. So just be careful about that. Don't always just write ln of whatever the denominator is. Okay, common mistake. The antiderivative of the right side with respect to t is k times t plus some constant. Here we have our logarithmic equation, and we know... Oh, that hurts. Sorry. Hold on. Okay, I knew that was going to happen. I usually turn that off. It's all right, and I've gone so far here. I don't want to stop. So there you go. We have a logarithmic equation. We're going to rewrite this as an exponential equation with the kt plus c in the exponent position. We know that the absolute value is here of y minus 20, and we know that we don't really need the absolute value bars now. In fact, I like to leave them there just to see what, just to show you what we just did, but then taking them away because e to some power is always going to be positive. And then we also remember that e to some power plus some other power, it can be written as e to the kt times e to the c. We get tons of flexibility because we know that any constant can be written as write as simple as we possibly can. And so we write that with a c, and I'm going to also add the 20 to both sides at the same time, giving us a function for the current temperature with respect to time as 20 plus c times e to the kt. So that's our current equation for y, but again, we also need to figure out what c is and also what k is, because both c and k are constants within this problem. All right, the first thing that's easiest to find would be the c. Okay, and we find c by letting t be equal to 0 and it says it takes 40 minutes to cool from 30 degrees to 24 degrees. So way back up here in our problem, we know that this 30 degrees is where we're starting. That's our temperature at time 0, and the other value there, 24 degrees Celsius, is our temperature at 40 minutes. Okay, so we'll use that in a little while, but the first thing we want to do is use this initial value, which is also what we've been talking about, an initial value of 30. So when t happens to be 0, so we plug in a 0 for t, we get 30 degrees. Okay, and now we have this equation here in which we solve for c. Okay, so all of this work takes a lot longer to explain than it actually does to do, and I usually shave off a few steps when I'm doing it on my own. C times e to the 0, which is 1, so c equals, and we subtract 20 from both sides, we get c equals 10. You'll find that this number here, 20, plus that number there is always going to equal the original, or the temperature at time 0. So we get y of t equals 20 plus 10e to the kt. So we're almost there. In fact, we do actually have our equation. We just need to figure out what k is. Okay, and the way we find out what k is let's see. I'm going to try to save a little bit of room right here and move on over here. So we're going to take this right over here. So if you remember, we found that at the 40-minute mark, we found that this object cooled down to 24 degrees. So we do know one piece of information, that at the 40-minute mark, which is 20 plus 10 times e to the 40k, that had a value of 24. So we can solve, now we have a new equation in which we can use to solve for k, because what we want that constant. It's called a growth or decay constant. In this case, it would kind of be a decay constant because the temperature is getting lower. And we want that value of k that would be constant throughout the problem. In other words, that's going to tell us how either quickly or slowly this object cools. So if we subtract 20 from both sides, we get 10e to the 40k is equal to 24 minus 20, which is 4. So we get e to the 40k, which is equal to 4 over 10. And then we take the ln of both sides. I understand that's 0.4. Take the ln of both sides, and let me do that. Ln of the left, ln of the right, and these two cancel each other out. Ln of e to the anything is the anything, and we get ln of, I understand that's 0.4. Okay, and so we get k is equal to ln of 0.4 divided by 40. And I'm going to put a little box around that, and I'm going to type that into my calculator. So let me get that. Like the 8.5 minute mark. Let's see if I can do this. Okay. So we have, again, the ln of 0.4 divided by 40. Is that what we had? Yeah. ln of 0.4 divided by 40. Okay, enter. Again, it's negative because the object is getting lower in temperature. And we're going to store that in alpha A. And I just have to remember where I store it. If you want to put a little a next to that, that would be okay also. A like that. So that's that value right there. So now that we have that, we can put a, let's see, where is that? Put a little box around the k, because our equation doesn't change. It's just that now we have a k there. That k represents our constant of growth or decay. So I'm going to pause here. I'm going to actually stop the video now and come back and show the rest.